Our bodies are engaged in a never-ending battle. Millions of bacteria, viruses, and fungi are constantly trying to make us our home. Thus, in order to ensure our survival, our bodies have evolved a complex little army, what we call the immune system, made up of numerous different cell types all working together to defeat the enemy. Within this immune system, we have what we call T cells. Their job is very similar to that of soldiers in a real army. They're constantly patrolling the body, checking our cells' IDs, and making sure that everyone's in line. However, if they encounter an ID that they've never seen before, they will launch a war on it. In order for the T cell to do its job, it first needs to be activated. And to be activated, it needs to interact with a different type of cell, what we call an antigen-presenting cell. This interaction is at the heart of the immune response, and it's of great physiologic importance. However, we still don't know exactly how the T cell is activated. We know in great detail all the physiological and chemical responses that are triggered during this interaction. However, this hasn't been enough. Recently, there's been a lot of research showing that the T cell is mechanosensitive and that the T cell receptor itself is a mechanotransducer. Basically, this means that it can feel the mechanical forces that are exerted upon it. It can translate these forces into a biochemical signal and then react to it. And this primarily what made us think that maybe the reason why we don't fully understand how the T cell is activated is because we've neglected the mechanical aspect for this process. And thus, the question addressed by my thesis is whether and how the mechanical forces acting during the T cell APC interaction are involved in T cell activation. So basically, what I've done during my PhD is try to design a substitute for the antigen-presenting cell to help us better understand this interaction. What I've designed is a super soft substrate. It has the same elasticity and the same antigens presented by the antigen-presenting cell. And in this substrate, I have a layer of fluorescent beads very close to the surface. When I add my T cells to the substrate, they're going to interact with it. They're going to push and pull on it, and they will eventually deform it. This deformation is basically the forces generated by the T cell. And since I have this layer of beads very close to the surface, when the T cell deforms the gel, it's also going to displace the beads. And if we track the displacement of the beads, we can then calculate the forces generated by the T cell and link them to T cell activation. Doing such substrates that are super soft is very difficult. I spent an entire year during my PhD just trying to perfect this substrate and characterizing it in every different way. And eventually I came up with a protocol that's quite reproducible and it's very homogeneous, and everyone else can use it at this point. What I would like to later do on in my life is maybe move away a bit from the fundamental sciences and use all the knowledge that I've gained and the expertise that I've learned and apply them to something that's more applicable, that's something that could really impact the world.